Hello. Oh my goodness. I can't tell that y'all are here. Hello. Welcome. 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 Yeah. Hello, everybody. Ooh, Kristen's here. Love it. And Kate. Hello. Hello. Welcome. Happy Cram. Happy first Cram. I'm so excited to be here. As we give everyone a minute or so to jump on, wanted to let y'all know we are going to do some problems tonight. So make sure that you've got some, if you want, you don't have to, but it would definitely encourage you guys to do the problems with me. So if you've got some paper and a pencil and maybe a calculator, definitely go grab that. We'll get started in a minute or so. If you're just coming in, welcome, welcome, welcome. Say hi in the chat. I was just saying that we are going to do some problems tonight. So if you are want to do some problems with me, then make sure that you've got some paper and a pencil and maybe a calculator or something with you. We'll get started in maybe 30 seconds or so. One thing that I do with my students in my classes is we always start with a first check-in question. So I always make it a fun question, and it's different every time. So we will do that here too. So today's fun question is, would you rather explore deep into outer space or the deepest parts of the ocean? And if you want to answer in the chat, definitely throw it in there. What do you think? You want to go into the ocean or do you want to go into space? If you're just coming in, welcome. Wanted to let you know we are going to do some problems tonight. So if you don't have some paper and a pencil and maybe a calculator around, might be helpful. We'll get started in just a moment. I want to make sure we've got everyone in. Great, 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 great. Both scary. Kate says both. Yes. I would definitely pick outer space if y'all are curious. Great. Life in the bottom of the ocean is more boring than aliens. True. That's so true. I would also pick space, definitely. Great. Well, great. Okay. Okay. We've got our first person to say ocean. The ocean, yeah, I don't know. The ocean's kind of scary. I think space is cool, but the ocean's scary. I don't know why. I'm coming at you from Boston, so I can see the ocean, but I don't know. Okay, cool. Let's get going. I am going to share some slides with you. We are talking tonight about our first unit, which is kinematics. So let me get these slides up for you. And perfect. Okay. So we are going to get started. If you're just coming in, just last reminder before I get started, grab some scratch paper. We are going to do some problems. You also have an awesome TA. Kristen is in the chat, ready to rock. She's been super helpful, forever, but definitely can be super helpful tonight. So if you have questions or want to, write anything in the chat, she's here and ready to help in any way she can. And we're just super lucky to have her. So with that, let's get going. A couple of reminders to start. First one is that we're recording this. So, you can get the Cram replay, but this is recorded for the replays and also might appear on the Fiveable website, YouTube, etc. And if you ask a question, your name will appear on the screen. So change your name if you don't want your real name on the screen. Great. And also definitely follow at Fiveable, Twitter, Instagram, YouTube. Learning is better when it's social, right? That's why we're all here. So if you have not yet followed Fiveable at those spaces, definitely take a moment and do that. We've got a lot of good stuff coming at you. Today, we are going to talk about kinematics. So really, we're going to spend a short amount of time at the beginning talking about one-dimensional kinematics. We'll talk about moving between position, velocity, and acceleration functions. We'll talk about kinematics. We'll talk about free fall specifically. And then we're going to spend most of our time today talking about two-dimensional kinematics, just because that's a little bit more challenging, I think, and probably something that you all maybe could use more help with. So we'll talk about vectors, vector components, and then spend some time on projectile motion. Great. So let's see. First, one-dimensional kinematics. So we've got a couple key ideas here. The first one is transitioning between position functions and velocity functions and acceleration functions. There's some math that goes with that, so we'll talk about that a little bit at the beginning. We'll talk about the kinematics equations, and then we'll specify or we'll zoom into specifically free fall and acceleration due to gravity. And we're just going to dive in. No time to waste. So first key idea in this one-dimensional kinematics side is these ideas of position, velocity, and acceleration functions. So because we are in physics C, there is some calculus that we can do with these functions, which is super cool. We know that to transition between a position function, which tells us about exactly what it sounds like, the position, the spot on the number line that the object is in, and the velocity function, which is telling us about how fast the object is going, and the acceleration function, which is telling us about how that speed or that velocity is changing. To go from position to velocity or velocity to acceleration, we're going to take a derivative. So this is a nice little bonus. We've got the calculus, and so the easiest way to do it is to just take a derivative between those functions. And I like to kind of think of it, because the exponents get smaller when you take a derivative. I think of like going position, velocity, acceleration, kind of going down the chart, and then you can also do the opposite. So if you've got an acceleration function and you're asked about velocity, you can integrate. And I think about that as going up, because the exponents get bigger when you integrate. That's just how my brain works. So in case that's helpful, I thought I would tell you. So to go from acceleration to velocity, we integrate, and then velocity to position, we would also integrate. Great. So here we go. We're going to do lots of examples tonight. So first one here, I'm going to give you a moment to do it, and we're actually going to do a poll. So this will be my first Vimeo poll, and I'm pretty excited about it. But here's our question. So it says the position of a particle moving along the x-axis is given as a function of time by the expression x of t equals t squared plus 8t plus 2. X is in meters, t is in seconds. What's the velocity of the particle at t equals 2 seconds? So I'm going to open up a poll. You all, if you want, can participate and see if you can get the answer to that question, and then go ahead and choose which one you think it is. I'll give you a minute or two to do the math and figure it out. And then I think if I do that, you should be able to, yeah, you're voting. Amazing. Great. So I'll give you a moment if you would like to participate in that. And then I'll show you, and we'll talk through the answer too. So if you're confused right now, don't be afraid. We're going to talk about it. I also talk through the silence. I'm not great at just letting it be quiet. That's not a thing that I'm good at. So as you're working, I'm going to probably just talk at you, which is probably not the most helpful thing, but I'll try and be quiet. But I think when we're just on the computer, I always like to just talk through that silence. So we've got some votes here. I'll give you another maybe 10 seconds, and then I'll show you the answer. They're looking great. All right. Amazing. So for those that participated, thank you. And this is what we see. So I think y'all can see velocity of the particle at t equals 2 seconds. And if I show you the results here, we all got it right. 1 for 1. Amazing. Yes. So good job. So if we want to talk through it, let me hide this back. Great. So we've got our position function. We need to find the velocity, right? So the first step here, I'm going to try and give you steps as we go through all of these different things. And the steps are usually going to be in black ink, and then my work will be in a different color. So first question we have to answer, or we have to ask ourselves is, what's the relationship between the function that they're giving you in the problem and the function that you're looking for? So in this case, I give you the position function. I tell you x of t, x is position, and you're looking for the velocity function. So we know that velocity is the derivative of position. So we need to just take a derivative. So we take the derivative of that position function. We get 2t plus 8. Remember, you kind of just go down an exponent and bring it to the front. And generally, I'm not going to go over a ton of the actual math part, really just the physics part, because I know that's the part that y'all are probably the most interested in. So we'll take that derivative. We get a velocity function, 2t plus 8, and then we want to answer the question. So in this case, it wants the velocity at 2 seconds. So all we need to do is plug in 2 for the time, and we get 12. Awesome. Okay, so then the next part here, here's another one. So we also can look at this in terms of a graph, right? And we need to be able to transition between the different graphs of these functions as well. So here's another one. This one we don't have a poll because it says draw a sketch, so we can maybe just think about it and then I'll show you the answer. So we've got a velocity time graph given to us for an object moving in a straight line. It's asking for a sketch of the position versus time and the acceleration versus time graphs. And I highlighted the word sketch because in AP, sketch is a very specific direction. So sometimes the test will say sketch, and sometimes the test will say plot. Those are two different things, and I want to tell you that because I don't want you to waste time, because sketch is actually a quicker thing than plot. When they say sketch, all you have to do is draw the general shape. You don't need to plot all of the individual data points. They're just looking for the shape of the graph. Whereas if it says plot, that's when you've got to actually make those, put some numbers on those, the x-axis and the y-axis, and actually plot some data points. So this one says sketch. So all we would need to do is draw the shape, which is faster typically, right? Because you don't have to actually draw everything out. So if we wanted to sketch for here, this is what it would look like. We've got a velocity time graph. To get the position time graph, we know we need to go up one. We have to integrate. So if I'm looking at the velocity, I see the velocity in that first part of the motion is 10 the whole time. It's constant, right? And we know that if we've got something that's has zero slope or is a straight horizontal line, it's constant. Then if we integrate that line, we'll get something that you can see on the graph where it's a line. It's a linear function that's got a slope that's not zero. The second part of the graph is a linear function. It's going up, that velocity is increasing. And so if that's happening, then we know we have to integrate up to a parabolic function. So you can see the second part of our sketch has a curve there, right? It turns into a parabola. And that's because that velocity is changing, right? Which means that the position is changing with that squared relationship. One thing that's kind of tricky sometimes is knowing whether or not that parabola should point like open at the top or open at the bottom. So like, is the position getting bigger faster, or is it kind of leveling off? We know in this case that because the velocity is getting bigger, the position is going to change more. So as the time goes on, that velocity is getting bigger, so the position is going to be changing faster and faster and faster. So we want it to open up. If the velocity was getting smaller, then it would open the kind of face down. For the acceleration, acceleration graph here, we go in the other direction, right? We take the derivative. So for that first part, that if we look at even if you just look at the slope of that first part of the line, we see that it's 0. So we know the acceleration has to be 0. And so that first blue line is on the axis because it's 0. And then in the second part, we see that it's got a positive acceleration because the slope of that line is positive. So it's a constant acceleration. So you've got some line that's not on the axis, but it's somewhere in the positive part of the graph, and it's straight. Cool. Okay. So then the next part, also a reminder, if you have questions about any of this, stick them in the chat. I can help, Kristen can help, we're both here. We're gonna move on. So the next part here is kinematic equations and free fall. So I wrote the kinematic equations out for you. This is what they look like on your equation sheet. They live on there, so you don't need to memorize them, but if you have them memorized, will make things go faster. And the only caveat with those is remember that it only works for objects with a constant acceleration. If the acceleration is changing, you have to do a new equation for each different acceleration that you have. And then the second part of this is free fall. Free fall motion is just kind of a specific type of kinematic or of constant acceleration. And it's when things are falling. So in this situation, we've got no air resistance. The only force acting on the object is gravity. So that means that it's going to be accelerating, but only due to gravity. So we have a very specific acceleration that we use every time. We call it g, little g, right? There's a big G too, but this one's little g, and it's always equal to 9.8 meters per second squared. We also know that if it's something that's a dropping problem, so if it's an object that it usually says it's dropped, starts from rest at the top and then falls towards the earth, then that initial velocity will be 0. If it's something, I always call it a a throwing upward problem, because one time I said throwing up problem, and that's right. So if it's a throwing upward problem, so the object is being launched straight up in the air, then at the maximum height, that velocity is going to be 0. So these are like little tricks that you can remember as you're going through the problems. You can also, if you just think about it, probably figure it out. But the more that I think that we can just be like, oh, I recognize this is a pattern, whether it's a dropping problem or a thrown upward problem or some of the projectile motion problems, I think the more efficient you can be on the test. So here's another question. We'll do this one again as a poll. So get your pencils ready. We've got a rocket. It's launched straight upward with an initial velocity of 30 meters per second, assuming air resistance is negligible. So that cues you that we're in free fall, right? Find the maximum height of the rocket. So I will give you a moment. I'm going to open a poll again, and while you all are doing it, I see there's some stuff in the chat too. Okay. I think you should be able to see it. Great, a couple of us are getting there. Take another 45 seconds or so. Great. Take another 10 seconds, and I'm going to show you. Awesome. All right, y'all. Wait, can I? There we go. Y'all, you're going to be so great. We're 2 for 2. Amazing. So I'll definitely talk through it. I also want to just shout out, a couple people put some stuff in the chat. Yeah, so Gregor says, pro tip on multiple choice questions, use 10 for G. It makes the math easy in your head. 1,000,000% agree. That's great. You'll get a close enough number that you can definitely get an answer. And yeah, Kristen's right too, for the question about acceleration being, if it's changing, if you're going to use kinematics equations, acceleration will be constant. Awesome. Great. Okay, so if we want to, let me show you the work here. So again, always trying to give you some concrete steps to take. So first one, always, when in doubt, write down what you know and draw a picture. That is my stellar picture of a rocket. Don't never claim to be an artist. All of these are going to be really not great. But I made my list of my 6 symbols and kind of tried to identify what are the things that I know, what am I looking for? Is there any tricks or tips or special kind of like, they're not secret, but I kind of think of them as like almost like secret zeros that are not directly in the problem. In this case, we know that at max height, that velocity is going to be 0. So that one's highlighted in yellow for you to be like, this one is maybe not obvious in the problem, but because we're awesome physics students, we know that at the max height, that velocity is 0. We know that the initial velocity is 30 because it tells us acceleration is negative 9.8 because we're in free fall. From there, we find out what kinematics equation we need to use. We plug in and we solve for y. When we're finding the maximum height, we're looking for a displacement, right? So we're looking for y. Cool. All right, so that's 1D kinematics. We're going to move on. We're going to talk about 2D kinematics. And again, there's really 3 key ideas here. So first thing we'll do is we'll talk about vectors and vector components. We'll briefly talk about reference frames. That one's not super relevant on the test, but I do want to just show you in case you come across something, kind of the most likely thing that you would see. And then we'll spend most of our time on projectile motion. So here we go. First, vectors and vector components. Key things to know once we add in that second dimension when we're talking about x and y together. We know that always, 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 we have to treat the x direction independently from the y direction. So basically, you're going to do everything in the x direction that you can. You're going to do everything in the y direction that you can. And then at the very end, you'll add the vectors together to create what we call a resultant vector, which is just kind of what happens when you put them together. So we can do that 2 ways. We can do that using something called graphic vector addition or analytic vector addition. Those are fancy words. The graphic vector addition is basically just making a triangle. And that's the one that I like to use. So that's the one we're going to talk about and use mostly tonight. If you wanted to use unit vectors, you can. All they are, if you haven't seen them, is, and again, it's one of those things where I want you to at least not be like, what is this, if you see it on the test. Sometimes we can write these vectors in like an equation, and we'll write the number of the vector, and then we'll write, it's called I hat. That's the symbol, like right here. We call it a hat. I don't know why. I guess it kind of looks like a hat. But I hat symbolizes the x component, and then j hat symbolizes the y component. And I'll show you an example in a second. We're going to focus on making a triangle, the graphic vector addition tonight, just because I think that that's both, like, I think a lot of students are visual, and like this helps visually, and it's easier, honestly. So when we do that, all we need to do is make a triangle with the x component and the y component using something called head to tail method. So if you look at the example triangle on the slide right here, the head of the vector, that's a technical term, is the side that doesn't have like the arrowy part on it. So I think you can see my mouse. It's this, if we're looking at the blue vector, the x component, it's this side. And then the tail of the vector is the side that's got like the arrowy part. I guess a tail, if you think about it like on a dog, like it's got a little extra thing on it. So the x component here, this is the head, this is the tail. So the way we do head to tail method is we draw the first vector, and then we connect the head of the second vector to the tail of the first. So basically we draw a cross, and then we connect the y vector up or down, depending on what direction it's going. And then from there, we draw our hypotenuse of our triangle, that's the red one, and that's our resultant, that's our answer. And then a lot of the time it's going to ask you for a direction too. And if it's not on in one of the, either like the horizontal or the vertical, then you're going to want an angle. And so we can use right triangle trigonometry to find that angle. So we'll do an example problem again to give you all some practice in a moment. Want to talk about reference frames just briefly. So reference frame definition is basically just the point of view through which you're measuring physics things. Most of the time you're measuring from the ground. So like pretty much everything you're talking about, we're pretending that the ground isn't moving and everything else is moving around it. But every once in a while, you'll be asked for something that is measured from a moving source. And so if that's the case, you have to take the fact that the thing that you're standing on or observing from is moving. You have to take it into account. So this is usually going to be like a boat, a plane, a car, anything that you like travel in, I guess, are typically the moving sources. And the why it matters, if we look at, I recently have, we recently bought Mario Kart on our Switch, and it's awesome. And so this is what inspired it. But if we look at the bottom GIF here, depending on whose car you're in, the situation is going to be different, right? If you're Yoshi's the green guy, right? If you're in Yoshi's car, it's going to look like Mario speeding up, moving past you, and then moving away. But picture if that you were sitting in Mario's car. If Mario's car was stationary instead, it would look like Yoshi was slowing down and then starting to go backwards behind you. So this is kind of a confusing topic. And again, we're not really going to spend a ton of time on like the concept part of it, because I don't really think that they ask you too much about that usually. The thing that they ask you, if they're going to talk about reference frames, they're going to talk about the example problem that we're going to do on the next slide. But just wanted to kind of give you a sense of why this matters. So here's the example. So we've got an airplane. It's flying east with a velocity of 900 kilometers per hour. And it's buffeted by a 20 kilometer per hour northern crosswind. So it says calculate the magnitude and direction of the airplane's resultant velocity. So one thing here, if it's a northern crosswind, it's coming from the north to the south. So that will matter because you're going to draw your arrow in a second. And the arrow should be pointing from the north to the south. And this is really, I think, the only situation that you'll see something with a reference frame. Because if we think about it, even though the airplane's flying with a velocity of 900 kilometers per hour, because of the wind, it's not going exactly 900 kilometers per hour. And so the question is, what's that magnitude and direction of the resultant velocity? So y'all can work on this. I'll open a poll. I also wanted to just point out that I wrote these vectors also in those unit vectors that I was talking about. If you were to do it, you see that it's 900 I hat plus negative 20 j hat. So that's the way you would write those if you were writing them in unit vectors. Just again, so that you've seen it before. So let me open the poll. Y'all are working on this. And Okay, so you should be able to work on this, and then when you've got it, go ahead and answer. I'll give you a minute or so. Take another 30 seconds. All right, I think we've got about the number of votes that we had last time. So I'm going to publish. Looks like we need a little bit of work on this one, and I'm glad. That's good. That means that we're here, and it's good. So let me show you. Show you what we got. So we're really close. Everyone got the number, which is great. What tripped us up a little bit, I think, was the angle. So let's look at how this works. So let me get rid of the, so y'all can see it. Okay, cool. So first step here, draw the vectors, right? So that's my airplane. Again, stellar artist. We've got the 900 kilometers per hour going to the east, because it tells us in the problem that the airplane's flying east. And then we've got the 20 kilometer per hour northern crosswind, so coming from the north, pointing towards the south. And so I think there's a couple of reasons that we could have gotten tripped up. One of them definitely could have been that we pointed that arrow in the other direction. And if that's the case, that's just like the problem, thinking more closely about what the problem is telling us. And that's like a super easy fix, right? The other thing is not really knowing how to get the proper angle, and that's what I'm going to talk about next. So we've got our two vectors. We're going to add them using head to tail method. So that's step 2. So we've got the 900 kilometer per hour east, the velocity of the airplane, and then we're going to take the head of the next vector to the tail of the previous vector. So that's that 20 kilometers per hour south. And then we're going to draw our hypotenuse. When you do that math, you do the trig, you definitely get 900.2 and you get the 1.27. So likely, I think, and definitely stick it in the chat if you've got a different question. Great. Yep, I see some questions. I'm going to answer them in just 1 second. So good. So you get that 1.27, and then there's a couple ways to answer it. Because it was, you had those 4 choices, the correct answer would be to find from the unit circle what that the angle is from the 0 part of the unit circle. I see some people referencing unit circle in the chat. So if we were to do that, I drew in green here. You can see that basically what we would do is we would do 360, which would be the whole circle, minus 1.27 to get that 358.7 degrees. I see someone in the chat saying, some people in the chat saying, you know, could you say negative 1.27 degrees? I think so. Could you say 1.27 degrees south of east? Yes, definitely. So I think it will depend on kind of what, you know, if it's multiple choice, what options you have, I guess. But if this is a free response type of question, I think any of those answers are good. And definitely, Kristen, chime in here too if you've got other experiences or thoughts. But I think that any of those would be good, because remember that the readers of the AP tests are really rooting for you, right? And all of those answers are correct. They're just said in a different way. So perfect. Okay, great. Let's talk about projectile motion. So this is definitely the most complicated part of the kinematics stuff. And the goal here is to first know what's going, like what is projectile motion, what's going on, and then try and find some patterns. So that way, as you're looking at projectile motion problems, you can quickly kind of figure out which thing is happening and act accordingly, set things up accordingly, right? Great, yeah, Kristen, thanks. So first, what is projectile motion, right? So it happens when we launch objects in the air and they travel in both the x direction and the y direction. It's a type of free fall motion. It's just not up and down. It's also left and right in the x direction. And there's kind of two big ones. We can either launch things horizontally. So think like launching horizontally off of a cliff or a building or something like that. Straight off, where there's no initial velocity in the y direction, it's all in the x direction. Or think launch at an angle, where you would shoot off, as you can see in these diagrams here, at an angle where you would have both x and y velocities. Great. And the nice thing is that really either one of these situations are just like more complicated, slightly more complicated free fall problems, because launching horizontally is basically a dropping problem with extra steps. And launching at an angle is basically a throwing upward problem with extra steps. So launching horizontally, the initial velocity in the y direction is still 0. The acceleration in the y direction is still negative 9.8. And the only difference is that in the x direction, you now have a velocity. And that velocity, we'll see in a second, is always going to be constant. Throwing up, or launching at an angle is just like throwing upward, where the velocity of the object at max height in the y direction is going to be 0. And it's going to start with some initial y velocity. So TA Kristen is awesome because she was like, you should put this diagram in here because it's awesome and it helped me so much. So I did, and I'm excited about it. So if we look at it this way, you can see this is a launch at an angle problem, right? You can see the arc of where the baseball is going. And at each point, we can see what's going on with the velocities. Notice that the velocity, the initial velocity in the x direction is going to be the velocity in the x direction the whole time. As a rule, the x direction velocity there's no acceleration. And so it's going to be the same the whole time. There's no forces acting on the ball in the x direction, so that velocity doesn't change. That's why. The only force acting on the baseball is gravity. So the only acceleration that's going to happen is going to be the acceleration due to gravity, which is only going to happen in the y direction because the Earth is pulling it down. So if you look at it, the velocity in the x direction is going to stay the same throughout the whole motion. And then in the y direction, you're going to start with some initial y velocity. And that y velocity is going to get smaller. At the max height, it's going to be 0. And then it's going to increase as you go down. And then assuming that you are launching and landing at the same height, then your initial velocity is going to be, or the negative of your initial velocity will be your final velocity. I also want to point out that as you've got right here your launch velocity, your initial velocity in each direction is just going to be your x and y components of whatever your launch velocity is. If you're given a launch velocity, you'll also be given an angle at which that launch velocity is, at which the object is being launched. And then from there, you can do the trig to figure out the x and y components of the velocity. Great. So setup. I like to give you as much concrete setup as I can, right? So here's how I would do it. You always encourage you to draw a diagram first, especially if you're like, there's a lot of words, I don't really know what's going on. Drawing a picture is super helpful. And then we need to keep our x direction and our y direction separate. So you're going to write down your 6 symbols in the x direction and in the y direction. Now you can see I put some notes in here because there's some again, tips and tricks for this type of motion. As we said, based on the last slide, the initial x velocity and the initial y velocity, the way we find it is we find the components of our initial velocity at an angle. If it's a horizontal launch, then the y component of the velocity is 0. So all of your initial velocities in the x direction. Also in the x direction, we just said it, the x velocity stays the same the whole time because the acceleration is 0. We give the x distance, so the distance that the object travels in the x direction, we give it a special name. We call it the range. So if you're asked about the range, you're looking for x. And then we know that the acceleration in the x direction is 0. In the y direction, we know there's less things that we know typically, but we do know that the acceleration is always going to be that negative 9.8 meters per second squared because it's a free fall. And the most important thing about all of this is that we need to keep x and y separate, but there is a connector between them, and that's going to be time. If you think about it, we know that as objects are flying through the air, they're going to travel for the same amount of time in the x direction as they are in the y direction. So if we can find the time in either of the two setups, in the x or the y, it's going to be the same in both. So that's really powerful because that's going to allow you to move between the x direction and the y direction. You get kind of double bang for your buck when you find the time because then you've got 2 more things to work with. Because you would always fill in that number for both columns. Great. So here's our first example. We've got an archer. It's going to shoot an arrow horizontally with a height of 3 meters and a velocity of v0. The arrow is going to hit a target that's flat on the ground. Which of the following is an expression for the position of the target on the ground? So this is I would say, a very typical multiple choice question for straight kinematics, because you're not just looking for a number. They like to just keep it in, expressions in terms of something else. And this time it's going to be in terms of v0. So work on this one. I'll open a poll again, see what you get. Give you a minute or 2 to do it, and then we'll talk about it. Take maybe 90 more seconds. I know this one's a little bit, it's going to take a little longer. There's more steps. Maybe 30 more seconds. I'm on teacher time. What that means is that I say 30 seconds, then it's another like 90 seconds sometimes. I don't know if you guys know that your teachers do that, but they do. All right, we've got a couple votes in. I think we're going to go for it. Okay, all right, let's see what we've got. If you didn't finish, that's okay. We're going to talk about it. This is definitely probably, yeah, I would say this is definitely the hardest problem so far. So let's see what we have gotten so far. So correct answer was the 0.78 V naught. And about 2/3 of us got it, which is great. So let's talk through it. Okay. So first here, when in doubt, draw a picture, right? So that's my arrow, and we know that it's going to get launched horizontally. It's going to travel some distance, and then it's going to hit the ground. The question's asking us for the position of the target on the ground. So what we're looking for ultimately is we're looking for X. We're looking for the range of the arrow. We need to fill in, after we've made our two columns, we need to just fill in what we know from the problem, which is not a lot, honestly, but it's enough to answer the question. So in the X column, we know that it's launched with a horizontal, it's launched horizontally, and it's got a velocity of V naught. Because it's launched horizontally, we know that all of its initial velocity is going to be in the X direction, so that our Vx naught and our Vx is going to be equal to, well, we're just calling it V naught. We don't know what it is, but we're calling it V naught, right? We know we're looking for X, and then we know that our initial X position, we'll just call it 0 because that's easy. And we know that our acceleration in the X direction is going to be 0 by rule, right? In the Y direction, we know that our initial velocity in the Y direction is going to be 0. It's launched horizontally. Remember, that's just like dropping, but in 2 dimensions. So our initial velocity in the Y direction is 0. We don't know our final velocity. We don't really care about our final velocity. It's not helping us, so I just left it blank. And then we need to think about our height. So it says that it's launched from a height of 3 meters. Whenever possible, I like to make the ground 0 just because that feels like it should just like make sense in my head, right? And so we know that if it's launched from a height of 3 meters, it's going to hit the ground, that its initial position is going to be 3, and then its final position, so our final Y, is going to be 0. And then we know, because it's in free fall, that our acceleration is negative 9.8 meters per second squared. So that's some info. Like I said, it's not a ton, but it is enough. So when in doubt, find T. So that's the first thing that I went ahead and did, is I found T, because T is the connector, right? So what I did is I plugged in what I knew in the Y direction into one of those kinematics equations. I simplified. I got an expression for, I got an answer for T. We know that T is going to be 0.78 seconds. So it's going to take 0.78 seconds for it to hit the ground. Then, because I look at my answers and I see, all right, well, I need an answer in terms of V naught. I know that V naught's in the X direction. I must somehow have to use my, the X values and find out what's going on in the X direction. We're also asked to find the expression for the position of the target. So we know we're looking for x. So ultimately, we're just going to solve for x. I can plug in my time. I know that my acceleration in the x direction is 0. So that's actually enough info to cancel out that whole last term of the kinematics equations and get an expression for x to be 0.78 v naught. Great. Again, reminder, if you have questions about this, definitely stick them in the chat. Okay. Cool. So I think this is, the last example. So we've got one more. Which of the following graphs represents the vertical component of the velocity of an object launched from the ground at an angle theta above the horizontal? So it's asking about an launch at an angle, and it's asking for just the vertical component of the velocity. So I think this is the last poll of the night. So let me open it up. And so you're just looking for which graph in this case is going to be correct. Take another 10 seconds or so. Okay. All right, last chance to vote, and then I'm going to publish it if anyone last wants to pick one. Okay, so here's what we said. Good work, folks. Yeah, so the correct answer is going to be B. Let's talk about it. So if we look at this, the way we think about it is we think about it in terms of shape, right? So an easy way to look at this to start is to be like, okay, so I know that if we're looking for the y component, we're looking for that vertical component of the velocity. It's going to be launched out from the ground at an angle theta. So first question is that y velocity 0? And the answer is no, right? Because we're launching at an angle. So there's got to be some initial y velocity. My second question I'm going to ask myself is that initial y velocity positive or negative? If we think about it, if it's launched at an angle, it's going to go up. So it's going to travel in the positive direction. So right off the bat, I know that my initial velocity in the y direction is going to be positive, and I can immediately answer B. If we want to dive into it more, we can think about it and be like, okay, so I know it's B, but let's just be sure. As it's traveling, is that velocity going to be getting bigger or smaller if it's getting launched up at an angle? And we know that velocity's got to be getting smaller because at the max height, it's going to be 0. So we know that the line has to be going towards the 0. It's got to be getting smaller. It's got to hit 0. And then as it falls, the velocity is negative, which definitely represents that graph B. So really just kind of picturing what's happening with the motion in your head, thinking about the direction is helpful, and thinking about key moments. So like the initial moment of the launch, what's the velocity going to be? At the max height, what's the velocity going to be? As it's hitting the ground, what's the velocity going to be? Those are all questions that you can ask yourself to try and when you're trying to think about graphs, and try and match up motion with graph. Think about key moments that you're looking for, or the sign of the velocity at different points. Great. Okay, let me check the chat one more time. Cool. Okay. So actually, look how well timed this is. So just a couple final things before I let you all go. When you're working on these problems, make sure to set your origin. That way you don't get positives and negatives messed up. So for that example, that arrow problem, we set the ground as our 0, right? So just being careful. Doesn't actually usually matter where you set your origin. You have to just be consistent in the problem. When in doubt, make a draw a diagram, list what you know and what you're looking for. That helps you to kind of unpack, especially if it's a word problem. I think that those can get the most like overwhelming at times. So just like unpack it, draw a picture, list the values that you know, list what you're looking for, and then just like write down an equation and see where it takes you. And then always, this is always going to end my slides, just like when you get freaked out, just take a deep breath. Breathing is like one of my, well, everyone likes to breathe, I hope, but like taking a deep breath is something that I do to calm down, and I hope that helps you too. And then you can do this and we can do this together. So next cram is going to be on Sunday, which is going to be the 7th. It's going to be at 5 p.m. Eastern time. We are going to talk about dynamics. So that's forces, Newton's laws. We'll talk about all of Newton's, all 3 laws. We'll talk about equilibrium. We'll talk about friction. Forces is kind of a big unit, I think. And so hopefully the next one will be helpful for you all. I know forces is something that my students struggle with a lot. So I'm looking forward to it. It's going to be great. And then very last thing is just you all are invited. Kristen's going to hop over to Discord, and we definitely should keep this conversation going. My favorite part about Fiveable is Discord. It's the community, right? We learn better when we learn together. So if you'd like, we are inviting you over there next to keep chatting. Join the AP Physics channel. And I think that's it. So I'll stop sharing so you can see me. If you have any questions, definitely stick around. But otherwise, thank you for being here. It's so nice to be with all of you, and I'll see you all next time. Bye, y'all. Bye, Matt. Bye now. Thanks for being here. Bye, y'all. Have a good night.